In the last few lectures, we have been discussing charges and their fields. We have discussed the Coulomb's law, electric field due to a charge, electric potential due to a charge, an electric dipole and its behavior in an electric field, and we have defined flux, we have stated Gauss theorem, and we have proved Gauss theorem, and we have dealt with many applications of Gauss theorem. In this lecture, we now start with current electricity, and the first topic that we have chosen is capacitor and capacitance. Now, the question is, how do we store charge on a conductor? By charging it a certain potential, but we cannot charge the conductor beyond a certain potential, because if we do, then the charge starts leaking and the potential does not increase. If the potential does not increase, then the charge that this conductor holds does not increase. If we want to increase, what do we do? That is the topic that we shall discuss today. In this connection, we have already learnt that the charge resides on the surface of a conductor. The electric field strength near a charge sheet, an infinite charge sheet, a large charge sheet, is sigma by 2 epsilon 0, where sigma is the charge density on the sheet, charge per unit area on the sheet. The electric field strength near the surface of a conductor is sigma by epsilon 0, because unlike the sheet, there is only one surface. Here you see, in the sheet there are two surfaces, here there is just one surface, the other surface, between the two surfaces there is a gap, and therefore, the field is only sigma by epsilon 0. All this we have already done. At points in between two parallel conducting sheets, except near the edges, the field has the magnitude sigma by epsilon 0. Let me remind you how we get it. The field to this sheet is in this direction, say red arrow, and it has a magnitude sigma by 2 epsilon 0. The field due to this sheet, because the charge is negative, is also in this direction inside these two sheets, say the blue arrow. So, and the field due to this in this direction is also sigma by 2 epsilon 0. So, therefore, at points in between two parallel sheets of opposite charge, the field at any point except near the edges is sigma by epsilon 0. Sigma by 2 epsilon 0 is contributed by the positive sheet in this direction, and sigma by 2 epsilon 0 is contributed by the negative charge again in the same direction. So, at any point in between the two sheets, the magnitude of the field is sigma by epsilon 0. Now, imagine a conducting plate carrying, say, a positive charge. So, we have a conducting plate carrying a positive charge. Suppose the plate is charged to maximum potential of a source. As I said, we can charge this plate to a maximum potential, and so we have done that. This is charged to its maximum potential. Now, bring a similar uncharged plate near this plate. Because of induction, you see negative charges developed on this side of this sheet, and on the reverse side positive charges develop because of induction. So, we have positive charges on this side, the far side, and negative charges on the near side of this original plate. And now, we earth the far side, so that all the positive charges on this plate, they vanish, they go to the earth. Only negative charges are left. These negative charges attract all the positive charges on this sheet. So, they appear now on a side which is opposite to this, on the side which is facing this. So, we have two sheets now facing each other, carrying positive charge on this side and negative charge on this side. And now, what happens? Because of this negative charge, the potential of this is partly balanced, and therefore, the potential slightly decreases. because of this negative charge, because of the attraction between these two kinds of charges, the potential of this sheet is slightly reduced. That means, we can push more charge onto this sheet, and we can therefore, what we have done is we have increased the capacity of this plate to hold more charge. So, an uncharged conductor brought near a charged conductor enables more charge to be stored on the charged conductor. This is the principle of a capacitor. Sometimes it is called a condenser. The capacity of a capacitor is its capacity to hold charge. If Q is the total charge residing on the capacitor and it is charged to potential V, then Q is proportional to V. The charge that is held is proportional to the potential difference between the two plates, or we can write Q equal to C V, where C is the constant of proportionality, and this constant of proportionality is called the capacity of this system. The SI unit of capacity is a farad, but farad is a very large unit. Therefore, usually we use microfarads, mu f. Now, let us see how a capacitor works. Look at the circuit shown here. We have a circuit here. When the DC source of voltage V is connected to the capacitor, it starts getting charged. The plate connected to the positive terminal accumulates positive charge, this plate, and this plate, the lower one, accumulates negative charge. While it is being charged, a transient current flows through a circuit, flows through the circuit shown by the glowing bulb. We have a bulb here, a current flows which is a transient, that means it flows for a very, very short time, and bulb glows only for that interval of time. As the potential of the capacitor increases, the current becomes weaker and stops altogether when the capacitor is charged fully to the potential of the source. So, if the potential of the source is the same as the potential of the capacitor, then the current stops. As we shall see later, the capacitor gets charged very fast. When it is charged the same potential as the source, the current stops as the capacitor behaves as a source. You see, the capacitor itself now is a source and sends a current in this direction, and therefore, it annuls the current due to this source, and therefore, there is no current in the circuit. Since the current flows for a very short time, it is said to be a transient current. In a DC circuit with a capacitor, there is no flow of steady current. That means, if we have a capacitor in a circuit, say in this circuit, then there is no flow of steady current. The current flows only for a very, very short time, and that is it, and there is no flow of steady current. Now, when the capacitor is fully charged, suppose we short circuit this source of potential, this battery. So, what happens now? Now, the capacitor will discharge through this resistance, and for a very short time, when it is discharging, the current will flow through the bulb and it will glow, but it is a very, very short time. There is no steady current, as I have said, in the circuit. This is important. Most electrical equipment and appliances such as refrigerators, air conditioners, microwave ovens, they have capacitors in them. Some of these capacitors can charge to very high potentials, very high voltages. When an appliance is unplugged, suppose I take out the plug of the air conditioner, it does not mean that the capacitor has been discharged. In fact, they may be storing substantial electric energy, and if you happen to touch it, you will get a huge shock. You are strongly advised, therefore, not to touch an appliance even if it is unplugged, because unplugged may have capacitors which are charged and which can harm you. Let only the trained persons handle these equipment. Capacitor is an important element of electric circuits, particularly AC circuits. Capacitors come in many forms. Simplest form is a parallel plate, two parallel plates or two parallel plates, parallel plate capacitor. Two conductors are side by side parallel to each other, and that in between there is a layer of either a dielectric or simply air. Air is also a dielectric. So, that is a capacitor. By rolling plates we can get cylindrical capacitors. If we have two plates and roll it, it becomes a cylindrical capacitor. Parallel plate capacitor is the easiest to deal with. Therefore, we derive the expression for the capacity of a parallel plate capacitor. We can have spherical capacitors where the two plates are spherical. There is in between there is either air or some dielectric. We can have cylindrical capacitor, but the easiest to deal with is the parallel plate capacitor. And this is parallel plate capacitor, as I have shown you many times. The charge, the field at a point in between these two parallel plates, as I have discussed already, is sigma by epsilon 0, and if q is the charge on any of these plates, then the charge density is q by a, where a is the area of this plate, and therefore, the electric field is q by a epsilon 0. And if V is the potential difference, then the field also has the magnitude E equal to V by d. Recall that electric field is the potential difference divided by the distance between the two plates. So, we equate V by d with q by a epsilon 0, and from this we get q by V, which we have already defined as C equal to a epsilon 0 by d. So, a epsilon 0 by d is the expression for the capacity of a parallel plate capacitor. D is the distance between them, a is the area of a plate, each plate, and epsilon 0, as you know, is the permittivity of vacuum. So, we have learned that the capacity of a parallel plate capacitor is proportional to the area of the plate. If this is the plate, then the area of this plate. It is proportional to the electric permittivity of the medium between the plates. We had air, but we can have any other dielectric, and it is inversely proportional to the separation between the plates. That is, if plates are nearer, the capacity is larger. The energy of the capacitor may be rewritten as W is equal to integral of V dq from 0 to q. You see, V times dq is the energy for the charge dq, and for the total charge q, the energy is integral of V dq from 0 to q, and this is half q squared by c. If is because V is q by c, so it is half q squared by c. And if we use the relation between C, V and q, we get energy either as half q squared by c, or as half C V squared, or as half q V. Any of these forms can be used. This energy is actually due to the electric field inside the capacitor. You see, between the two plates there is an electric field, and this electric field provides the energy to the capacitor. Let us look at this energy density, energy per unit volume. A is the area of the plate and d is the distance. Therefore, A times d is the volume of the capacitor. So, therefore, the energy per unit volume is W by A d, which we have called U, and it is half C V squared by A d. Now, if I substitute C equal to A epsilon 0 by d, we have derived this formula, and recognize that V by d is nothing but E, then you can write U as half epsilon 0 E squared. And if you will see later also, this is the energy density due to the electric field in the medium of permittivity epsilon 0. So, the energy to the capacitor energy is provided by the electric field inside it. If air is replaced by dielectric of permittivity epsilon, then the capacity of a parallel plate capacitor becomes A E by d. The derivation remains the same, which we can write as epsilon by epsilon 0 into epsilon A by d. Epsilon A by d is the capacity when there is air in between or vacuum in between, and epsilon by epsilon 0 is the relative permittivity K, dielectric constant. So, the capacity when there is a dielectric in between the two plates is K times epsilon 0 A by d. That means, the capacity is enhanced by a factor K, it increases, and that is why most capacitors where we need large capacity, they have materials like mica or paper between the conducting sheets. Now, the question arises, how does the introduction of a dielectric increase the capacity of a capacitor? How does it do that? To understand this, let us look at the process of charging a little more minutely. So, as soon as the contact is established, the circuit is complete. What happens? The electrons from the battery, which are produced by chemical reaction, these electrons travel to this plate, negative plate. The electrons from this are pushed out, and therefore, it develops a positive charge, and these electrons again travel to the positive plate or positive terminal of the battery and go inside the battery and recirculate it again. So, there is a build up of negative charges here and a build up of positive charges here. This build up of negative charges or positive charges, particularly this negative charges, prevents further flow of electrons to this plate. So, when this is fully charged, this electron flow stops. These electrons flow to the positive terminal of the circular. As the negative charge builds up on the plate B, the electrostatic repulsion impedes the eventual and eventually stops the further flow of electrons to it. At the time of flow of charges stops, the potential on the capacitor is equal to the voltage of the source. The capacitor is fully charged. We now introduce a dielectric plate. So far it was air, now we introduce the dielectric plate. The polar molecules of the dielectric plate are polarized because of the electric field inside the capacitor. We have positive charge here, we have a negative charge here, we have the electric field, and this electric field polarizes the molecules of this dielectric. And how are they polarized? The positive charges are separated from the negative charges, and positive charges line up to the right towards the negative charge, and negative charges line up towards the positive charge. That is how they are polarized. And what happens? This positive charge cancels with this negative charge, this positive charge cancels with this negative charge, and this layer of positive charges remains, and this layer of negative charges remains, as we have shown here. So, the dielectric has a layer of positive charges here and negative charges here, and therefore, an electric field which opposes the electric field that means the effective electric field in between the two plates is reduced. Therefore, the potential can be increased further, and if you increase the potential of the plates, obviously you can push more charge. So, therefore, the presence of a dielectric in between the two metal plates of the capacitor increase its capacity. You see, I have already told you this, that this field due to dielectric opposes this field, and therefore, the potential difference is reduced and the capacity increases, Q by V it increases. Suppose that there is a slab of dielectric constant K and width T. In the whole space was covered by a dielectric. Now, we have only a plate of thickness T dielectric inside the capacitor. So, what happens now? Same thing, field d d is there in this direction, field D is there in this direction. So, field E is present in the space which has a thickness d minus T in this and in this, which is d minus T. So, the potential difference due to this would be E 0 into d minus T. Inside the dielectric, the field is the E 0 is the field difference between E and E d. This E 0 is present in the distance d minus T, and the total potential and the potential in this side, inside this is E 0 by K. You know, the potential reduces by a factor of K, the dielectric constant. So, the total potential difference between the two plates is E 0 d minus T plus E 0 by K times T, because the effect of the field has decreased through factor K, the dielectric constant. So, V is there, and if I use E 0 as Q by A epsilon 0, then I can find Q by V, which is capacity, and this takes the form A epsilon 0 by d minus T plus T by K, and you can see that the presence of T increases the capacity. And when the slab is conducting, then there is no field inside a conductor. We have learnt only in the last lecture, in which we discussed the Gauss theorem, that inside the conductor there is no field, and therefore, this term T by K vanishes, and we have the capacity equal to A epsilon 0 by d minus t. T by k vanishes because there is no field, there is no field in this region because there is a conductor. Now, if several capacitors with capacitances C1, C2, C3 are arranged in series, then the effective capacitor is given by the reciprocal of the sum 1 by C1 plus 1 by C2 plus 1 by C3. And if they are in parallel arrangement as here, then the effective capacity of the capacitor is C1 plus C2 plus C3. That means, if they are in parallel arrangement, the capacities get added up. If they are in series arrangement, then the capacity gets reduced. It is equal to 1 by C1 plus 1 by C2 plus 1 by C3, and if we add them up and then take the reciprocal, that gives the effective capacity. Say this, for example, this exercise is for you. You see, here we have plotted Q against V, and there are two curves, and what we had were two capacitors. They have certain combination, and we have to find which line corresponds to which combination, line A or line B, which of these corresponds to, for example, the parallel combination, and which corresponds to the series combination. Remember that Q by V is C, therefore, the slope of these lines is the capacity. Now, since the slope of line B is smaller than the slope of line A, that means B, this line B must correspond to the series combination of capacitors, where capacity is reduced, and A must correspond to the parallel combination of capacitors, because the parallel combination increases the capacity of the system. In this example, we have 4 capacitors. 3 of them, C1, C2, C3, they are in series. Why are they in series? Because the negative plate of this, for example, joins with the positive plate of this, and then the negative of this is joined with the positive of this, and so on. They are in series, and the effective capacitance due to C1, C2, C3 is again in parallel with C4. So, we can 1 by C1 plus 1 by C2 plus 1 by C3, and reciprocal of that would give the capacity of this series combination. So, that is C effective, and then this is C4, and this is potential V, and C4 we can find the values, and the C effective is 6 by 11 of C. Now, C4 and C effective, they are parallel, they have the same potential, and this charge on this, and by the same token the charges on C1, C2, C3, they are the same as on C effective. And what is the charge on this? C effective times V, and the charge on C4 is C4 times V. So, you can find the ratio of the two charges, and this ratio is 3 by 22. You can calculate. This is another important thing. We have two capacitors C1 and C2. They are charged to potentials V1 and V2. Then they are connected. I connect the positive of this to the positive of this, and negative of this to negative of this. That means, they are in parallel combination. So, the total capacity is C1 plus C2, but when they are allowed to transfer charge from one to the other, then the charge gets transferred, but it stops when the potential of the two is equal. So, when capacitors are connected, the charge flows between them till a common potential is reached. Then the charges on the two capacitors are, when the common potential has been reached, Q1 would be C1 V1, initially Q1 is C1 V1, Q2 is C2 V2. The total charge is therefore Q1 plus Q2, which is C1 V1 plus C2 V2. Total capacitance of the capacitor is C1 plus C2, because they are in parallel arrangement. Therefore, the common potential is total charge by total capacity, C1 V1 plus C2 V2 by C1 plus C2. Now, the initial energy is half C1 V1 squared plus half C2 V2 squared, and the final energy is half C1 plus C2 into V square, and we can substitute the value of V from here, and then we can find out the difference between the final energy and the initial energy. if you do some algebra, you will see that the difference between the final energy and the initial energy is this, which has V 2 minus V 1 square. So, whether V 2 is larger than V 1 or V 1 is larger than V 2, it is a positive quantity. Therefore, this one is always a positive quantity. That means, the difference between final energy and initial energy is a positive quantity. So, the charge on the capacitor C 1 is C 1 V 1 and on the capacitor C 2 is C 2 V 2. The total capacity is C 1 plus C 2 because they are in parallel arrangement. Therefore, the common potential is C 1 V 1 plus C 2 V 2 divided by C 1 plus V 1. Initial energy is half C 1 V 1 square plus half C 2 V 2 square, and the final energy is half C 1 plus C 2 V square. And by finding the difference, we can find out if the initial energy is higher than the final energy, or if final energy is higher than the initial energy, we can find the difference. And we will see that in such an arrangement there is always a loss of energy, and this energy gets dissipated mostly as heat. In the above problem, if the two were connected in series, then they were allowed to have connection between them, then the charge would be C 1 V 1 minus C 2 V 2, the total charge, and therefore, the total charge is Q 1 plus Q 2 equal to Q, and the common potential is equal to Q 1 by C 1 equal to Q 2 by C 2, and we can solve these equations and we can get Q 1 and Q 2, and we can find out whether the energy increases or decreases. Finally, we have this example. You see, this is an infinite arrangement of capacitors. Each capacitor is 1 microfarad. Now, if the arrangement is infinite, it is obvious that if I do not take this into account, it does not matter, because it is infinite arrangement. If I take 1 out of 1 million, it does not matter. Therefore, all this arrangement has, let us say, the capacitor C effective. Then our system becomes this 1 mu f, which is in series with this C effective, and then the two are in parallel with this capacitor 1 microfarad. So, we can now find the capacity of this system, and this must be equal to C effective, because C effective is the capacity of the infinite system. So, we set up the equation, and this equation is that 1 by 1 plus 1 by C effective, which is the capacity of these two, and this must be equal to plus 1 plus this must be equal to C effective itself, and therefore, we can solve for C effective and we get two roots, 1 plus minus root of 5 by 2. Capacity cannot be negative, and therefore, we accept the value 1 plus root 5 by 2. So, this infinite system of capacitors 1 microfarad each has the capacity equal to 1 plus root 5 by 2. The negative sign, of course, has been neglected, because the capacity cannot be negative. In this lecture, we have dealt with capacitors. We have first learned the principle of a capacitor, then how the introduction of dielectric increases the capacity of a capacitor, and then we have learned that the capacitors in series, their capacity gets reduced, capacitors in parallel, their capacities are added up, and then we have done a few examples. In the next lecture, we shall now start studying the electric current, and the first thing we shall do is to learn about resistances.